Okay, I've got another one of my favorite sorts of problems on the board. Okay, so S is a portion of a cone, x equals y squared plus z squared. So that's similar to the cone that we're used to working with, which opens up. The difference is this one's going to open forward. So instead of the z-axis being along the center, now it's the x-axis that's cutting through the center. Okay. All right, it's the portion of the cone behind x equals 4. So this front portion right here would be where x is equal to 4. Okay. And it's oriented out, so that would be away from the center of the cone, like so. All right, C is going to be its boundary curve oriented positively with respect to S. Okay, so I can see that C is just a circle that I'm looking at straight on. It's maybe easier if I actually take this model of a cone. So we'll say that this right here is that circle in the plane x equals 4. Now it's a little bit tricky getting the orientation using the right hand rule here. I can sort of say if I use my right hand and I come like so, the normal vector seems to be pointing straight out, but it looks like that would end up inside of the cone, right? Whereas if I come around this way, I can see that, oh, my thumb is going to be outside of the cone. So that sort of suggests that this is what I want. So looking at it from the forward direction, it would be going clockwise. Might be helpful here to remember the other characterization we had for orienting a curve relative to a surface. If this is oriented out, the outside surface is going to be the positive side. So somebody who's walking around this boundary is going to, if they're going in the correct direction, is going to have that surface on their left. And that will be true if they're walking around on the outside. If they were on the inside walking around the boundary in that direction, this would be what's on their left. Or if they were to walk around in the other direction, walking around like so, now the surface is to their right instead. We want it to their left for their orientation. So I know that I want this circle to be oriented clockwise, looking straight on. Okay, so I will draw that in. So that's clockwise as we look forward. Okay, then I've got my lovely vector field, and we're going to calculate this integral, but we're going to do it 2 ways. So first we're going to do it as a line integral, just using the definition of line integrals. And then we're going to use Stokes' theorem to do it again using an appropriate surface integral. And I'm about to erase this, so I just want to call attention to how I phrased it. I did not say using Stokes' theorem to evaluate a surface integral over S. I said using Stokes' theorem to evaluate an appropriate surface integral. So if we can find a nicer surface that has the same boundary, we are allowed to use it. Hint, 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 that's what we're going to do. Okay, but let's do the line integral first. So if I'm going to do the line integral, let's see, I want to keep up that vector field so I don't forget what that is. If I'm going to do a line integral, I'm going to need to parameterize this curve. I do need to remember that I'm in 3 space. My x value is going to be fixed because this is where the cone hits that x value. And if this was the square root of y squared plus z squared is equal to x, and x is equal to 4, that essentially tells me that this is going to be a circle in the plane x equals 4, which is parallel to the yz plane, a circle of radius 4. So if I'm looking in the yz plane, I'm looking at a circle of radius 4 that when I look at it straight on, goes like so. Now, in this picture, y is in the place that I'm used to having x, it's the horizontal axis, and z is in the place where I'm used to having y, it's the vertical axis. I know if in any plane parallel to the yz plane, I want to be going clockwise, I want the vertical axis to be defined to be my sines. So I'm going to let z equal 4 sine theta and y equal 4 cosine theta. I'm sorry. I'm so used to writing thetas that I wrote thetas. We'll go with t. Doesn't matter, I could go with theta, but then I'd have to write theta there. We'll go with t. Okay, I can double check. If t is 0, I would be at 4, 0, 4. So I'm forward 4, I'm in the plane x equals 4, but y would be 0 and z would be 4, so I'd be up here. If t is pi over 2, I'm going to be at 4, 4, 0. I'm going to be here. So yes, we are going clockwise. Okay. So there's always the trial and error method. If you got it wrong, then you can switch it around. Okay, excellent. So with this, if I now go to evaluate the integral along C of f dotted with t ds, oh, I should probably say that I'm going to restrict t to being between 0 and 2 pi. So this is going to become the integral from 0 to 2 pi. I want to write f in terms of my parameterization. So x times y becomes 16 sine t. 2z becomes 8 cosine t. And y, of course, is 4 sine t. I'm going to dot that with r prime. And r prime, I can see, is just going to be 0, 4 cosine t, negative 4 sine t. And then we'll integrate that dt. So let's go ahead and evaluate that dot product. So it's the integral from 0 to 2 pi. I'm going to get 0, and then I'm going to get 8 times 4 is 32 cosine squared t minus 16 sine squared t. And we're integrating all of that with respect to t. Okay, so I'm going to just copy down what f was here so that we have it for later. Okay, and now let's clear some space so that we can evaluate this. So I know if I'm evaluating an even power of sine or cosine, I'm using the double angle formula for cosine. So I'm going to have the integral from 0 to 2 pi of 32 times cosine squared is 1 plus cosine 2t over 2 minus 16 times sine squared is 1 minus cosine 2t all over 2. And we're integrating all of that dt. Okay. Those are formulas we've done often enough this semester that at this point I've got them accidentally memorized. If you don't, make sure you know how to derive them. Okay. All right, so let's see. I'm going to just cancel some stuff here. So that's going to give me 16 times 1 plus cosine of 2t minus 8 times 1 minus cosine of 2t dt. Let's go ahead and distribute that on through. So integral from 0 to 2 pi, 16 plus 16 cosine 2t minus 8 plus 8 cosine 2t, integrating all of that dt. 16 minus 8 is going to give me 8, and then I've got 16 plus 8, which would be 24 copies of cosine 2t. All right. That's a dt. I am going to do a quick u sub here. Okay. So I'm going to let u equal 2t. So then du is 2 dt. Okay. So I can pretty much factor out a 2 since that goes into each of those. So if I do that, we'll be going from 0 to 4 pi. If I factor out a 2 to absorb into the du, I'm going to be left with 4 plus 12 cosine of u du. So that's going to be 4u plus 12 sine u, and that's evaluated between 4 pi and 0. Okay, so 4 times 4 pi is 16 pi. Sine of 4 pi is just 0, so I'm adding 0. And when I plug in 0 to either of these terms, I'm just going to get 0. So we get 16 pi. All right, I'm going to write that down up here, because what we're going to do in the next video is we're going to come back and we're going to use Stokes' theorem to evaluate this as a surface integral instead.